Hey everybody, welcome to section 12.4, the cross product. The cross product is a quantity we compute between two vectors. It's also known as the vector product because the result is a vector. All right, so if we're given two vectors, vector A, and the cross product is only defined in 3 dimensions. If we're given vector A with components A1, A2, and A3, and vector B with components B1, B2, and B3, then the cross product is another vector and it's found by, ready? So it's a vector, so I'm going to use this pointy bracket notation. It's all computed using components. The first component of the cross product is the second component A2 times the third component B3 minus B2 times A3. That's going to be the first component of the new vector. The second component is going to be A3 B1 minus B3 A1. And the last component is going to be A1, B2 minus B1, A2. All right, woo. Okay, just a fact or a theorem, the cross product of vectors is another vector. Okay, and interestingly, this third vector that you just created is going to become perpendicular to the two given vectors. Perpendicular to both A and B. So if we have two vectors in space, let's suppose we have the pink vector and the purple vector, like floating in space like this. Right, so if we were to find their cross product, it would be a third vector perpendicular to those two, like this. Okay, or it could point in the opposite direction. All right, so let's find the cross product for V and W, where V is -136 and W is 425. You just gotta be really careful. It's tedious, easy to make mistakes, so V cross W. We use the cross here to indicate that we're taking the cross product. Well, the first component is going to be A2 times B3. So it's going to be -15 minus B2 times A3, so -12. The second component is going to be A3 times B1, which is 24, minus B3 times A1, which is going to be +5, right? Nope, it's going to be minus, and that's going to be there, so don't make that mistake. -1 times -5 is going to be, so it's going to be 24 minus +5. And then the last one is A1, B2, so it's going to be -2. And it's going to be B1 and A2, right, -12. So the vector would be -27, 19, -14. So if we were to put these three vectors in 3 dimensions, like floating in space like this, then the cross product would be perpendicular to all of to those two given vectors. Sorry, did my best to try to do that in video. All right, properties of the cross product. By the way, I do have a cool way, if you could, not that you have to memorize this, but I have a cool way to compute a cross product. It just takes way too long to write down. But if you want to see it, feel free to zoom in. All right, properties of the cross product. The cross product does not commute. If we reverse the cross product, we get this relationship, okay? So it does not commute. Reversing the cross product produces a different result. If we have a constant, we can move that constant around in a cross product. We could just take the vector U and take the cross product of that with C times V. Or we could pull the C out and find the cross product first. So we can move constants around. A cross product with a sum, as long as we stay on the left side, everything, if it's on the left, it has to remain on the left. We can distribute a cross product through a sum. So the cross product of U and V plus W is just the cross product of U with V plus the cross product with U with W. If we have the vector on the right, we can distribute it on the right too, as long as we leave the vector on the right. So it's going to be the cross product of u times v plus v times w. Right, the dot product with the cross product. Well, the dot product with the cross product, well, we could take the cross product of u and v, and then the result, that with the dot product. If we have a cross product of a cross product, so it has some funky properties here, we could take the dot product of u and w. Oops, I think I lost a thing here. I'm gonna have to get back to that one. I'm thinking I lost something here. So that would be maybe cross product right there. There we go. Standard basis vectors and cross products. Remember, standard basis vectors are vectors that are parallel to the x, y, and z axis and have length 1. If we take the cross product of I and j, it's going to give us vector k. All right, so if we are in the x, so here's the x, y, z plane, right? Trying, let's see, right there, right, like that, x, y, z plane. So I would be the purple cap, j would be the green cap, and the cross product would be k in the positive z direction, which is, I don't know if you can see that, but it's the pink cap. If I switched it and I did j cross I, it's going to point down. It's going to give us negative k down below. If we take j and we cross it with k, so that's the vector parallel to the y-axis. This is the vector parallel to the z-axis. It's going to give me the unit vector parallel to the x-axis. If I switch it, if I do k cross j, it's going to still be parallel to the x-axis, but pointing in the negative direction. I cross k, parallel to the x-axis, parallel to the z-axis. It's going to give me the unit vector parallel to the y-axis. And if I switch the order, it will be parallel to the y-axis, but pointing in the negative direction. Right, and lastly, the cross product, u times v equals the vector 0 if and only if the vectors u and v are parallel. So we saw using the dot product, if we can determine if vectors are perpendicular, because their dot product would be the scalar 0. If vectors are parallel, then their cross product is the vector, the 0 vector. All right, and lastly, the magnitude of the cross product. This is a theorem, can be proved using trigonometry. The magnitude of a cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. And when we talk about angles between vectors, we always talk about the angle between 0 and pi. So for example, here's two vectors, u and v in space. There's this angle between them, and there's also this angle between the vectors. And we typically talk about the one that's less than 180 degrees. One common little side note, if you put two vectors in position such that they're tail to tail, or initial point to initial point, it creates a parallelogram. And the area of this parallelogram is equal to the magnitude of the cross product of the vectors. All right, that's it, kids. That's just your introduction to the cross product. Have fun, and I'll see you later.